Hello everyone, and welcome to a screencast about visualizing your data using proto-repl-charts. Proto-repl-charts is a plugin for the Atom text editor, and it's the sister project of proto-repl, which is the premier REPL for writing closure code within Atom. And today I'm going to show you how to use that combination to create great looking visualizations of your data and hopefully understand more about the system that you're working with and the data that it's using. So let me explain a little about proto-repl. Now, for those of you that already have an Atom closure development environment set up, I'm going to put a link so you can skip past this bit, but this is going to get everyone else up to the same place where you can write closure code and execute it in the REPL within Atom. So proto-repl is a REPL development environment. It's written by Jason Gilman, and it's a fantastic piece of software. So we're going to get that installed, and we're also going to install the proto-repl-charts package, which is what enables you to do the visualizations that we're going to be doing to get a visual overview of different kinds of data. Great. So those are the cool kind of charts that we're going to be creating. So let's jump over to Atom and let me tell you the packages that you'll need to get started. So the two that you absolutely have to have are proto-repl and proto-repl-charts. You can find them by searching under install for proto. Turn off cap lock. Proto. Should come up. Yeah, there they go. They come up as the top two when you search for proto. I've already installed those. There are a couple of other packages that I recommend when you're doing closure development in Atom. Par-infer is the top one. It's the magical utility that figures out where all the brackets should go. Very, very useful. Inc is really great because you can do inline REPL evaluation results using Inc. I use list par edit to make sure that the next line indents where you want it to. There's minimap to overview the code. What else do I use? Set syntax and recent files fuzzy finder. So grab all or some of these and create a new Liningen project. And you want to include both proto-repl and proto-repl-charts as dependencies in your project. You don't have to include proto-repl to run a REPL, but what doing this allows you to do is have great code completion, which is super useful. So I always add proto-repl to any projects I'm working on, and then you need to have proto-repl-charts so you can pull in this visualization that I'm going to show you. Okay, so that's the project setup. Let's jump in and start writing some code then. So I'm going to show you 4 different kinds of charts or 4 different ways of visualizing your data, and hopefully you'll start to understand what kind of data visualizes best in what kind of way, and also hopefully you see how useful and cool this is as a way to see your data and see the shape of your data. So let's start with a bar chart, and let's start by writing a function that's going to generate some random data for us. So let's write a function that rolls a single die given a number of sides of that die, so a single dice. And what we're going to do there, so we're going to do a random int based on the number of sides, and we're going to have to increment it because it's 0 indexed inc. Okay, so we'll execute that. So now we have that function. So now if we run that repeatedly, so we roll the dice repeatedly, let's say we roll it 100 times, roll die, and we pass in, let's do a 6-sided die, and let's run this. Okay, and we get this back. So it's a list of all the different rolls that were performed. But it's kind of hard to get a feeling for the shape of that data. It's hard to see the distribution. So let's switch to paren mode, and let's do reduce. No, let's do frequencies. So let's figure out how often each one of those. Let's switch back to indent mode. Great. So let's run that. Let's figure out how often each one of those numbers turns up. Okay, so now we get, using the frequencies function, we get a map that maps from the number that resulted and how many times it turned up. But even here, it's kind of hard to sort of see the shape of the data, even though there isn't much. So it's useful to be able to get this inline feedback in your code. Of course, people that don't have a REPL or REPL-based development, they're probably jealous already. But with proto-repl-charts, and let's just pull it in, you could do, if you have a namespace and you've got proper code, you can do it as a refer, but for now we're just going to use PRC, proto-repl-charts. Let's evaluate that. Nil. Okay, and then we can just surround this function in PRC slash, we want a bar chart, and we give it a name, so let's call it dice frequencies. And then we just need to move this in so it gets included, and let's run this. And great. Now we've actually got a visual overview of how often each number has rolled during that 100 roll set. And if you hover over, you see in reverse order starting, so number 3 was the most common number to come up and 6 was the second most. And you can then examine individual numbers. But you see that you can see the shape of the data in a different way than just seeing it in a frequencies map. And by the way, it's using the C3 charting library. It's a JavaScript library that creates charts based off of the D3 visualization library, at least for these type of charts. For the, I think it's the graph charts it uses Vis.js charts, but we'll get to that later. Okay, so we're starting to see the shape of the data, but what happens if we create data that has a slightly more useful shape than this? Because if we increase the number of frequencies here and run this again, we're going to start to see that this just flattens out, and that's kind of a boring shape. So let's create a slightly more interesting shape by having a function that can roll several dice. So if we take the number of sides first, and then we take the number of dice, and then we do this repeatedly, just like we did before, and then we do it the number of dice, and then we run the function roll die, and we do that for the number of sides. Okay, so we repeatedly, for the number of dice, roll the die for them. That looks right. However, we don't want to get, because this is going to give us a list of the different rolls for each dice, but we want to actually add them up. So let's do that. So let's do a thread last, and let's just do a reduce plus. So that each time we roll a set of dice, we're just going to get a single number, the sum of all of the different rolls. Okay, so let's execute that. So now we have a roll dice function. Let's bring this back to 100. Instead of doing roll die 6, we'll do number of sides, then number of dice. So let's roll 2 6-sided dice 100 times. Let's get the frequency of that. So, and I didn't talk about this, but the bar chart function, it's expecting a map. So it's expecting a map from the data point to a frequency, or to a number on the y axis. So which is perfect, because that's exactly what frequencies provide you. So when you have data that's frequency type data, a bar chart is a great way to show it, because you don't need to do any manipulation to the data. It's already in the shape that, okay, and now you start to see that we've got a bit of a shape here. And if we increase the number of runs again, so if we go to 1,000, let's go to 10,000, and yeah, this isn't going to blow your mind if you've taken even a basic course in statistics, then you know that this is a pretty standard normal distribution, and you understand that rolling dice, 2 dice several times is going to get you a normal distribution. But still, I'm not trying to blow your mind with the maths of this. What I'm trying to blow your mind with is how useful it is to be able to visualize your data in this way, to see shapes, to take advantage of the fact that the human pattern recognition and visual system that's evolved over millions of years is something that we don't really use very often when we're programming. And I think that's a real shame, because it's something that we're so strong at as human beings, but when we're working with our code, we're just writing text and getting back numbers, and we're not using that ability we have to see these visual patterns and to understand shapes of things. Okay, so let's look at another way to visualize the same kind of data, and this time we're going to do a scatter chart instead of a bar chart. So if we pull in prc/scatter chart, give it a name, so we're going to use the same dice function. So let's call this dice scatter, and let's pull that back. And this is also expecting a map, and it's expecting a map from a group of data to that data's results. So let me explain quickly what that looks like. So if we grab, yeah, that's fine. Let's grab that one for 6. So let's only do 100. So we're going to repeatedly, so we're going to do 100 times in the test group, and we're going to take a 6-sided dice and we're going to roll it twice. So that's fine. And let's do one that's going to give us slightly bigger numbers. So let's repeatedly 100, roll a dice that has 10 sides, and let's roll it 3 times, which should give us a slightly different distribution. And the scatter chart is going to give us It's not a time series chart. It's almost like each let me run it and I'll show you what it looks like. Okay, here we go. So you can start to see that we've got 100 iterations on the bottom, and on the x-axis and on the y-axis we have the range of numbers that we got. And you can see that the distribution over time, the blues are more widely spread and they're higher up, and that's because it's a larger dice and we're rolling more of them, so you're getting more of a spread. So let's try the same thing with an even larger spread. Let's say we have a 20-sided die, and let's paste that in again. And let's do a 20-sided die lots of times. How many? Let's do it 5 times, let's say. Okay, so we've got 3 groups of data, 6, 10, and 20, and you can see how you can isolate one particular group. And let's do 1,000 times. Let's give ourselves a bit thicker data, a bit more points to view on the chart. Okay, here we go. So 6, 10, and 20. And you see what I mean, that you start to see the shape of the data. You see how they relate to each other, and you get a sort of an intrinsic understanding of what kind of values you're getting from this random data. So you understand that 6 is this fine band between, I guess it's 2 is the lowest you can get, and 12 is 12 the highest you can get. Yes, yeah, 2 and 12. So it's a really nice way of visualizing your data. And of course, if you have random data, maybe it's not so interesting to visualize it. That was just to generate the data quickly. But when you're thinking about the data in your system, when you're visualizing it, maybe you have sequential data that isn't random, where there are going to be really interesting patterns that are going to crop up. So that's where this could come in really handy. Okay, let's look at another type of graph that we can create using proto-repl-charts. And that is a graph. So if you have data that it has relationships between the data, then a good way to visualize it can be using a graph or a directed graph. And as luck would have it, proto-repl-charts has that under the function named graph. And this doesn't use C3, as you can see here, it uses biz.js. But that doesn't really affect much because you use it in basically the same way. So you still pass it a name. And we're going to do a family tree graph. And in fact, we need to pull that in. So if I go to my clipboard history, and let's grab, yeah, here we go. So we have this data structure, parents to children, and it's a map of vector to vector. And the first vector are the parents, and the second vector is the list of children. So we have 3 different families in this. So let's evaluate that. Okay, so we have this family tree. So a graph is expecting a map, just like the other ones, and expecting a map where you have all of the nodes in a list and the edges in a nested vector. So it's a list of all of the relationships. So let me just quickly show you what I mean. So if we have A, B, C, and we have an edge between A and B, let's see if this renders correctly. If we run that, yeah, there we go. So you see we have 3 nodes, and it's rendered the relationship between A and B. So what we need to do is generate a list of all of the people in this family tree, so both parents and children. So let's take the parents to children map, and the first thing we could do is we could pour it into a vector, or we could use the seek function. If we run this, it should give us, yeah, so it's given us everything as nested vectors. And now we just need to flatten that. If we run that again, okay, now we have all of the people, but we have Eddard twice because he's been a naughty boy here. So let's do a distinct. And let's run that again. Tywin, Joanna, Xerxes, Sansa. Yeah, that looks good. Okay, so now we have all of the nodes. So if we do that without describing any relationship, so we have an empty vector of vectors, and run this. Okay, so there we have the whole family, but without any relationships being shown. Tywin and Tyrion, and you can pick them up, and they have, it uses a physics engine, so they interact with each other. Tyrion and Tywin are, curse your sudden but inevitable betrayal. So he's gone. Anyway, you could have fun for hours just playing around with that. But let's try and figure out how we can actually calculate all of the relationships. So what do we need to do here? Well, we could do nested maps or nested list comprehensions. So let's start with the innermost list comprehension. So for each parent, if I could type, and if it's going to be nested, I guess, should we nest it in let's nest it in a map, and then we can just grab the key out of each. So each time, so remember the data structure we have at this point. So we have a map with vector to vector. So if let's do the outer map. So if we map over that with this, and let's put this one here. So we're mapping over parents, children. So for each time that this gets something, it's getting a key value pair, and the parents are the key, and the children, let's call it child, is the val. Put that there, let's put that down there. Does that make sense? So map parent, let's run it and see what happens. Arity, wrong number of args passed to core map. Why is that? Oh, because I didn't do this correctly. We're not doing anything within the for, so we actually want to return a vector of parent to child to capture the relationship. Let's close that and let's bring that back because that's what we're mapping over. Does that make any more sense? Let's try that again. Okay, this looks good. So what do we have here? Oh no, that didn't work. Why is that? Oh, but if I flatten it by doing a map cat, would that work? Doesn't matter where that one is. Let's try this. Tywin. Yes. So we just need to flatten it with the map cat. So we've got Tywin to Cersei, Tywin to Jaime, Tywin to Tyrion, etc., etc. Looks good. So we've done a map cat. The inner for, we're grabbing each parent and child combination, storing the relationship in a vector, and doing that over all of the parents and children. Makes sense. So let's run this whole thing. And there we go. We have the families. Eddard and Caitlyn's family, and you see how the physics works even with the edges as well as the nodes. And we have the other family on the other side with Joanna and Tywin. But you'll notice that the layout doesn't make it super easy to see the relationships. This is just the default way that Vue.js is rendering the relationships. But as luck would have it, we have access to all of the same customizations that you would have if you were writing this in JavaScript. So in fact, I think this was quite heavy to customize this to look good. So we can go back to the clipboard and here we go, nodes, font size. Yeah, this one. So we can describe a different font size for each of the nodes. We can change the edges so that they have arrows to with a scale factor of 0.5 and from, so they're going to point to each other. We can change the layout to be, instead of this default layout, some kind of flow. I can't remember what it's called, but we want it to be hierarchical. We want to separate each level. We want it to be an up-down direction, and we want it to be sorted by directed. So if we run this again, hopefully it starts to look a bit more like a family tree, and we can zoom in. And you see how it looks with the edges, and you can still move them around. So that is kind of neat if you have data that has relationships. Yeah, and you see how John sticks out on the end there. Willa, I don't know how you pronounce that. Okay, and let me just show you that you can do different directions. So that's an up-down direction. Let's try it with the left-right direction. Okay, same idea, but just rendered this way. Maybe that's better when you have a vertical pane like this. Cool. So that's graphs. That's directed data with relationships. I'm going to show you one more type of chart or graph, and that's a time series. So that's when you have data that has a time element involved. C3 understands time or dates if you tell it the format that they're in, and then it can help you. So let's open up. I think I have a CSV. What was it called? Time series? No. Haven't opened it recently, clearly. Was it resources times? Here we go. Okay, so it's a classic CSV file. It's data from, I think it's some kind of a stock exchange, because it has open price, a high price, a low price, and a close price, and the volume of trades during that day. And you see the date is in the year, month, day format that's common in Europe. So we have this CSV file, so let's slurp it in. And it's resources, if I could type, I wish I could, time series.csv, but it's not capital T. Okay, so if we just run that, let's just check that we get the string. So we get a single string with all of that. So we're going to need to do some processing, because C3 and or proto-repl-charts can cope with rendering data in either row format or in column format. So this one, oops, if I can swap back to time series, it's in row. So the data for each date is in a row, not in a column. So let's call this, let's def row data as, and let's do some processing on it as well. So let's do, let's do thread last, let's slurp it. And in fact, we're going to want to split it based on the commas. So let's do thread first then, and then let's grab this and let's do a closure.string/split, and let's split it with a regex that is, was it commas and new lines and anything else that I want to split it on. No, commas and new lines should work. So let's do comma and new line in a conditional like that. Let's see what that, let's run this bit and just see that gives us what we expect. Let's just move this out of the way a bit. Yeah, that looks good. It's all split up nicely. Perfect. So now we have our row data, but not quite, because we're going to want to partition it to make sure that each row is actually a row in this data. So let's grab this one and let's partition it by, how many was it that we have? 1, 2, 3, 4, 5, 6. So let's partition it by 6. Let's try running that whole thing and see what that looks like. Yes, so now we actually have a list of lists where each list is a row, and the first row being the names of the columns. So that looks good. Now we have our row data. So now we want to do a time series chart. And if we go to PRC, you'll notice that there isn't one here called time series. But that's not going to stop us, because we can use a custom chart, which means that we can make use of any of the charts that C3 supports. So if we go here and we open up C3.js, so this is the charting library that's using for the bar, and it supports all of these line charts, time series, spline. So let's look at time series. It's a bit slow to render, but you see that there are the dates along the bottom, and it's figuring out the distance between the dates, etc. Given in this one, it's using column data, but we're going to do row-based data because that was how our CSV looked. So let's go back to Atom. Okay, let's give us some space here. Just like the other ones, you give it a name. So let's call it time series. Bring it back, and again, this is expecting a map. Won't be a surprise to you, and it wants a map that's the data, and we have row data. So we use the keyword rows, and let's pass in our row data. Nice, and it wants us to tell it what the x-axis is. And if we look again at our data here, let's run this. The x-axis is called date. And anything else we need to give it? Yeah, we need to tell it that it's a time series. So as well as data, let's tell it about that the axis should be of type. So the x-axis is of type time series. And then it knows to look for the date, but we also then need to give it the format for the tick. So tick format, and then what was the format of our date? It was year, month, day. So percentage year dash percentage month, and it's the lowercase month because it's just a 2-digit one, and it's percentage day again lowercase because it's the 2-digit version. Okay, so let's try running this and see what we get. Compiler exception, runtime, row data. Okay, we never evaluated row data. So now we have row data. Let's run this. Aha, and we have a time series. Oh, but I see a problem straight away, and the problem is that volume is huge and all of the other ones have gotten compressed to nothing. You can't see the shape of them because, yeah, you see the difference in the magnitude of the data. One is in the, is it millions? 50 million, is it? 5 million. And these are down at 100. However, that's not a huge problem because C3 supports multiple y-axes. We just need to tell it about it, so let's do that. So let's say axes, and then it's another map, and then we need to tell it the name of the data, which if we come back here and run this again, what was it? It was the last one, I can't see it, it's off the edge. Volume with a capital V. So that's the data that we want to create a new axis for. So volume, and let's give the axis a name. Let's call it y2. It's the second y-axis. That's good enough. And then we need to define. We've already defined how the x-axis looks, but let's define the y2 axis and what's different about that. So we want to show it. So we set show to true. And maybe that's enough. That should work. So it's volume with y2. We've defined y2. We want to show it. Let's try running this. Ta-da! That worked nicely. Let's spread this out. We can lower this down as well. So you see that the volume is now being rendered or measured against this right y-axis, which is in a totally different scale than the left one, which is where all of the open, high, low, and close are rendered. And you'll also note that even though the dates aren't evenly spaced, so there are bigger gaps between certain days, because it's a time series chart, it understands dates. So it understands that the 17th and the 13th are 4 days apart and renders them 4 days apart, which is really useful. So again, we start to see the shape of the data. You can compare the data. You can see only the high, only the low, only the close, etc. And again, I'm not expecting that you're looking at stock exchange data daily when you're doing your closure programming, and that's not the point of showing you this. It's more that if you have data that has a date component, then time series can be a great way of visualizing it. Okay, and that was everything that I wanted to show you really. So we've covered bar charts with the dice frequencies, seeing the shape of frequency data in a nice way. We've covered scatter charts for plotting sequential data, so data that changes over time, or in this case, iterations of this random function. We've talked about, well, it's a bit slow to render, but we've talked about the graph, directed graph data types when you have relationships, visualizing those, and we've talked about time series when you have dates in your data. So what I'm hoping that I've sparked in your mind now is you thinking about, well, what kind of data am I using in the systems that I work with on a daily basis? And what's a nice way that I could use this tool to visualize that and help me understand it? So if so, that's a big success. There's one final thing I wanted to tell you about. If you like this, the color scheme that I use here, there's a theme that I've released on atom.io called Borealis. So if you want to install it, you go to install, and instead of searching for packages, you search for themes, and you search for Borealis. It should come up. Borealis syntax, a dark theme with pastel colors. So that's the one I've been using. And that was it. I hope this has been useful. I hope you enjoyed it, and I hope you go forth and visualize all your data. Thank you very much for watching this, and see you around. Thank you, everyone. Bye-bye.